Hello again. So Nikolaj Mücke is our PhD student in the project, in the Indo-Dutch project, and I realized that it's getting later and later in India now, right? And it's a pleasure to have Nikolaj give his talk in this context, and he will talk about reduced order modeling for fluid simulations using deep learning. Nikolaj, the floor is yours.
Yes, thank you. Do you all see my slides?
Yes.
Perfect, perfect, perfect. Yeah. So my name is Nikolaj, Ph.D. candidate at CWI, and I'm going to talk about.
Nikolaj.
Sorry?
We don't see it yet in full screen.
Okay.
Double click.
I do.
Okay. Okay.
Is okay. So I'm just going to continue, or?
Yes. Okay.
Okay. Cool. Cool. Yeah. So I'm going to talk about reduced order modeling for fluid simulations using deep learning. This is joint work together with these two handsome gentlemen, Kees Oosterlee and Sander Paté, both from CWI. I'll firstly give a brief introduction to the problem and then move on to talk about dimensionality reduction and then latent-space dynamics, and then show some results for two test cases. I might skip one of them depending on the time. So what we're dealing with are fluid flows, which are often modeled as time-dependent partial differential equations. The usual procedure to solve such problem is to make some kind of spatial discretization using finite element, finite difference, finite volume, or whichever method is your favorite method. From there, you would usually do a temporal discretization, either with a Runkuta method or multi-step method, or well, something else. So basically what you end up with is a finite dimensional discrete dynamical system which is defined by the right-hand side function. We will in this talk assume that we can achieve arbitrary precision using these kind of methods, meaning that if we refine in space and time, then we can get infinitely close to the true underlying analytical solution. And we will call these solutions the high fidelity solutions. One thing that's important to notice is that this high fidelity solution and problem is in general very high dimensional. So we are not only going to consider time-dependent PDEs, but also parameter-dependent. So in this case, we assume that the problem and the solution is also dependent on the parameters, which leads to what we call a solution manifold, which is a manifold of solution parameterized by the parameters. So the problem with these kind of problems is that they are inherently very time consuming to solve, especially if you are looking at multi-crew problems such as uncertainty quantification, state estimation, model predictive control, inverse problems, and so on. Then you would often have to solve this problem, parameter and time-dependent problem, within an outer loop that would either optimize some objective or estimate some distribution or something like that, which means that you will have to solve the high fidelity problem a lot of time. In my talk, I will only focus on solving the high fidelity problem and not incorporate any of these multi-query problems. But in general, the point is that real-time solutions are practically impossible in these cases. So what we want to do, as Jan Hesthaven talked about in the first talk today, is we want to perform reduced order modeling. Here, the idea is that we assume that the solution manifold can be approximated by reduced order model. It is sometimes referred to as a surrogate model. Sometimes they are referred to as two different things. I will just use the two words interchangeably. So the general idea is to divide the computations into two stages. An offline stage in which you will compute the reduced model, and then an online stage in which you use the reduced model to solve the multi-query problem. As is shown in this figure at the bottom of the screen. The offline stage is computationally quite heavy, but once it's done, then you can hopefully solve the problem very quickly for many parameter settings. So this talk is also about deep learning, which has become very popular lately due to the approximation abilities of neural networks. They can approximate almost every kind of function, and they're extremely versatile, which I will talk about later. I will not go into details in the different kind of networks I use, but rather mention them and talk about what are the advantages of using the kind of networks that I'm using. Oh, I see, I've got a point here. Specifically, I'll be using neural networks for dimensionality reduction and for time stepping. It should say time stepping below dimensionality reduction here. So let's get started. So in dimensionality reduction, the idea is that we can embed the solution manifold into a lower dimensional latent space. And in this talk, I will use the word latent space. Often specifically in scientific computing circles, you would call this the reduced space or reduced order space. But in machine learning communities, it's latent. And yeah, so I just chose to use that terminology today. The idea is that you define an encoder and a decoder. The encoder takes in a high fidelity state and encodes it into the latent space, in which you can then do computations. But of course, the encoder is not worth much if you can't get back to the high fidelity state. So you also need a decoder. So in an ideal setting, those two will be inverse of each other. The way we usually compute these encoders and decoders is a data-driven approach by computing snapshots using the high fidelity solver, and then minimize some function, and then minimize some difference between the high fidelity and the encoded decoded state. So typically, most common is a linear dimensionality reduction. Here, the encoder and decoder are linear operators, or in a finite dimensional space, they are simply matrices that project your vector onto a low dimensional space. The most common approach is using the proper orthogonal decomposition, which uses the singular value decomposition. And here you define your encoder as being the first NL left singular vectors. However, it has been shown in many cases that this approach does not work well for heavily nonlinear problems and for advection dominated problems, which is why we want to look into nonlinear dimensionality reduction. Again, the fundamental idea is the same, but instead of encoding the state onto a linear manifold, we now assume that the latent space can actually be a nonlinear manifold. That of course makes the encoder and decoder more complicated, but you can typically encode your state into a much lower dimensional manifold. Common approaches are methods such as kernel, PCA, or neural networks, as I talk about in this presentation. So specifically, I will be using convolutional neural networks. They are specifically good for spatially distributed states and for images, as we see here, this lovely cat. The general idea is that you assume that degrees of freedom that are close together are more correlated than degrees of freedom that are far away from each other. We see that we make use of that hypothesis by using a filter and moving that across the picture. And then by using nonlinear activation functions, we get the nonlinearity. Specifically, I am using convolutional autoencoders, which is a special case of convolutional neural networks, where you take the original data or original high fidelity state, and then you compress it by using convolutional layers, and compress it even further by using dense layers until you have a latent representation of your state of dimension that you would like. And to decode it, you basically do the same, but in reverse by using deconvolutional layers and go back to a reconstruction. So in the training, you are basically training the encoder and decoder to be the inverse of each other. So it is not enough to simply reduce the dimension. You also want to advance the state in time in this latent space, which is why we want to somehow come up with a way to define latent state dynamics. Here, the idea is that there exists some map FL that advances the reduced state in time. So it's basically the same as the discrete dynamical system you get from a Runkuta discretization. But here, since we are not in the original space, we have to define a new function that advances the states correctly. In general, this function, FL, is not easy to identify. And there are, in general, two approaches to defining this, this dynamic map, time-stepping map. An intrusive approach is arguably the most common one, where you use a Galerkin projection to project the high fidelity model onto the low dimensional space, which is really nice because then it is to a much high degree, to a rather high degree, interpretable, and you can derive stability estimates. However, it is not always the case that the model you are considering is available. For example, if you're using black box solvers, such as OpenFOAM, or if you only have data available, then this procedure is not possible. Furthermore, in the online stage, it can actually be expensive because, especially in nonlinear cases, you often have to go back and forth between the high fidelity space and the latent space. There do exist methods that overcome this, but they are not always effective. So instead, what I want to present is a non-intrusive approach based on neural networks. So here, we choose to approximate the time-stepping map by a neural network. So we basically define a neural network that takes a state one step forward in time, and we train this on snapshots and simulations of data generated by the high fidelity and the autoencoder models. This approach is much more flexible because it works with basically all kinds of model, which is not entirely true, but it's almost true. And you can use data and simulations for the training. However, you do miss some interpretability, and it may take a long time to train. Furthermore, we want to increase the accuracy by including not just the current state, but several previous states in order to predict the next stage. This can be compared to methods like multi-step methods, where you use several previous states to increase the accuracy. The way we do this is basically encoding the previous states using a temporal encoder, and then from there we advance the state. I particularly looked into two different time series encoding neural networks. One is called causal convolutional neural networks, and the other one is called LSTMs, long short-term memory neural networks. Both of them are very efficient in encoding memory, and they are highly versatile, and they allow for nonlinear encodings. Furthermore, they do not assume any model structures, so they do have the same advantages as normal neural networks as being universal approximators. But as I said, we are not only interested in advancing the states based on the previous states, but we also want to incorporate parameters such as diffusion rates, Reynolds number, boundary condition, initial condition, or that could basically be anything. So we also need to encode the parameters. So we do that by encoding the parameters in a separate network from the time series encoding. And from these two encodings, we make a prediction to the next state. So in summary, we have a network that consists of two separate independent networks. One that reduces the dimension, the convolutional autoencoder, the convolutional encoder, sorry. And from here, we can advance the latent state by using our time-stepping network. In each state, if we want to, then we can decode and get back to the high fidelity state, if that is what you want to do in your application. The nice thing about this is that once you have trained the time-stepping network, you can advance the state from basically anywhere by just supplying the time-stepping network the previous latent states, which means that you have very large flexibility and can use it together with many different outer loop techniques. For example, in state estimation, where you would make one-state predictions and adjust it by, for example, using a Kalman filter. So I would like to say a few words about the training. In general, we would like to encourage generalization and stability. And by generalization, I mean that we want the network to be able to perform nice on data that it has not seen during the training. We do this by regularizing the weights of the neural network. Secondly, we want to encourage stability. And by stability, I mean that we want to ensure that errors do not accumulate in time. To do this, we know from discrete dynamical systems theory that large eigenvalues of the Jacobian of the map leads to unstable dynamics. So we want to minimize the eigenvalues of the Jacobian. But since the eigenvalues are incredibly expensive to compute, we regularize the Frobenius norm, since the Frobenius norm bounds the spectral norm of a matrix. And we consider beta 1 and beta 2 as hyperparameters, which leads to the next point of hyperparameter tuning. What I did here was use a Bayesian hyperparameter tuning technique that search the hyperparameter space efficiently. And as for hyperparameters, I consider the number of layers, the number of neurons, the regularization parameters, the learning rate in the gradient descent approach, and the batch size. So basically the usual hyperparameters in deep learning. So to summarize, in the offline stage, what we do is compute a series of high fidelity snapshots with your PDE scheme. From there, you train a convolutional autoencoder to reduce the dimension. Once you have the autoencoder, you can reduce states and train a time-stepping neural network to advance the latent state in time. Once you have these two networks, you can go to the online stage, where you would need to compute the first n states, use high fidelity methods, because the latent time-stepping scheme needs several previous states. From there, you will reduce these states by using the autoencoder, and then you can start advancing in time by using the time-stepping neural network. And lastly, once you have computed your latent space trajectory, you can decode it back to the high fidelity space. So I have included two test cases in this talk. One is a rather simple linear advection case, a 2D linear advection, where we have a space-dependent velocity. For the high fidelity solver, I used a discontinuous Galerkin finite element method, a second order scheme, and an implicit Euler time-stepping scheme. For the initial condition, I considered a Gaussian profile and varied the location of this Gaussian profile. For the parameters of the problem, I consider the location of the Gaussian initial condition and the velocity of the advection. For the training of the neural network, that was the wrong numbers here. It should say parameters here, and it should be these numbers. Sorry. I trained the neural networks on 80 trajectories, and I trained it for 3,000 time steps, not the 2,000 here. And then for the network, I sampled only every 6 steps, so the neural network could take longer steps than the high fidelity solver, resulting in 500 steps in total. So here we see animations of the neural network and the high fidelity solutions. And at least qualitatively, there's basically no difference. We see here in the table that in the high fidelity method, we have around 21,600 degrees of freedom, while in the neural network using the autoencoder, we can go down to 2 degrees of freedom. And computation time-wise, we get a speed up of around 266 times. And we achieve an accuracy around 10 to the power of -3. We see here the dimensionality reduction compared to proper orthogonal decomposition, that with the neural network, we can get precision down to 10 to the power of -3 by using a latent dimension of 2, while using Ph.D, we need 16, 17 dimensions. Furthermore, I compared my method with similar approaches, such as Ph.D together with Gaussian process regression and Ph.D together with decision tree regression. And we see that none of the other approaches are able to actually capture the dynamics effectively. So that speaks in favor of using these rather complicated neural networks to do this. So I would like to show off a more advanced test case, which is the flow past a cylinder, which is much closer to a real-time setting, and which has much more interesting dynamics. We look at the incompressible Navier-Stokes equations and the typical flow past cylinder problem. It is discretized using a finite element, Taylor-Hood elements, and a second order splitting scheme to deal with the nonlinearities, and an implicit Euler stepping scheme. Furthermore, I chose to only focus on a sub-area of the full domain for several reasons. One of them is to show that with this framework, you do not have to spend time compute the full domain if you're only interested in a subdomain, which is very difficult to do in with a full order model. Secondly, I have saved dealing with geometry and for a later time for now. Yeah, I parameterized the problem by the Reynolds number and look at Reynolds number between 120 and 200. So in this regime, we get some very nice nonlinear behavior. We get a vortex street, but we do not move into turbulent territory yet. I trained the neural networks on 30 trajectories, and I trained it and I computed 15,000 time steps with the high fidelity solver and sampled only every 5th step, resulting in the neural network being trained on 3,000 time steps. So here are simulations, the neural network to the left and the high fidelity to the right. And as for the linear advection equation, qualitatively, there are basically no difference unless you look really closely, I guess. We were able to decrease the degrees of freedom from 73,000 down to 4. And the computation time, we get a speed up of around 260. Accuracy is slightly lower than the linear advection, and it's between 10 to the power of -2 and 10 to the power of -1, which in some cases might be unacceptable, but this, as we see on the next slide, is mostly due to a slight phase error, which is apparent here in the top right corner. So Here I have taken a snapshot of the very last state and compared the neural network with the high fidelity. And I have zoomed in on the area right behind the cylinder. And again, qualitatively, there's very little difference. The neural network, as I said, is computed with 4 degrees of freedom, which results in an encoding decoding error of 10 to the power of -3. Compared to, for example, proper orthogonal decomposition, we need between 60 and 80 Ph.D. modes to get the same accuracy. If we look at one specific point and plot the evolution of the velocity magnitude in time, we see that they have that the neural network approximates it very well, but is slightly off when it comes to phase. And we see here that the evolution of the error in time does oscillate a bit. The shaded area is due to the area computed. The error is computed on a set of several Reynolds numbers, and then I've computed the standard deviation of the error at each time step. So, for future work, I want to develop the framework further by looking into how we can impose stability so we can go even further in time. Furthermore, I want to test it on more complicated problems closer to real-world applications. And I want to combine it with these multi-query settings as I described earlier, such as uncertainty quantification, inverse problems, and state estimation. And even later, I want to incorporate real-world data so we not only rely on a high-fidelity solver, but actual observations as well. And lastly, as was mentioned by Case, this project is part of a grander scheme of developing a digital twin for pipe flow. So of course, I want to apply this framework to pipe flow settings and to develop in the long run a digital twin that's able to detect leakages and compute multi-phase flows, and even compute on larger pipe flow networks, as has been described in earlier talks today. So thank you very much for your attention, and you are all free to contact me using this email. Yeah, that was it for now.
Thank you very much, Nikolaj, for a very nice and interesting overview of your work and a very good presentation. I see in the chat already 2 questions, so let me ask them to you. One is from Alien, and he asked, are the encoder and decoder completely separate, or can you gain an advantage from having the encoder to get the decoder?
So they are not completely separate, because when you train the autoencoder, you train the encoder and decoder simultaneously. But once it is trained, you can decouple them. So you can basically decouple any, decode any state, and you can encode any state independent from the other. But in the training, they are not separate. Okay. Did I understand the question correctly here?
Yes, yes. Then a question from Enrico Camporeale. Have you tested the neural net for any case in which one of the parameters, the Reynolds numbers, the boundary conditions, what was not used for training?
Mostly no, but there's a slight but, and that is in the sense of initial conditions. So, for example, in the advection problem, the initial condition is parameterized by a parameter, but the parameter does not solely describe the entire initial state. The initial state is described by this Gaussian profile. So mostly, I would answer mostly no, but it is very interesting.
Okay.
Yeah.
Okay. The question from Mike Botchev. First of all, he congratulates you on your talk, and then he asks, why do you need a neural network for advancing the reduced order model in time? The reduced order model is probably small and easy to integrate with Runge-Kutta.
Yeah, so the problem is, and that is the question about intrusive versus non-intrusive. So when you have the reduced state, you don't get the reduced model for free. So if you want to use, for example, Runge-Kutta, then you need to define the right-hand side of the dynamical system. And the problem is the right-hand side for the reduced state is not available unless you do something like a Galerkin projection, for example. But that requires access to the full order model such that you can project it onto the latent space. So it is definitely a good question, but I would say it's just another library of methods, which we call intrusive methods. I have seen work done where they combine autoencoders and multi-step and Runkuta schemes, where they project the high fidelity model onto the latent space. But again, that requires access to the high fidelity model.
Okay. I'll take the questions that are now on the chat. One is, for training, do you have to run 30 high fidelity test cases?
Yeah, if you want to train on 30 trajectories, you can of course use more or less. The number of test cases that you would use for training is not an easy question to answer, because it is in general very problem dependent. So what I've been doing is I would start out with a small amount of trajectories and see how well my model perform. And if it does not perform well, then I would generate more test cases, which is the nice thing about using a simulation data for training, that you can generate, in theory, as much data as you need. And you can generate the data in parallel. Yeah.
Well, for sure, two more questions for you, Nikolaj. One from Shashi. Is there an intuitive way to see where the physics is being incorporated in a neural network? No, there's the short answer is no. There's no intuitive way, unfortunately. And in this work, I have not incorporated the physics into the neural network. It is purely data-driven on simulated data. The only thing that vaguely resembles physics incorporation is this Jacobian regularization. But that is more of a numerical analysis-based argument rather than a physics-based argument, if that makes sense. Mm-hmm. But I'm definitely planning on, in future work, adding physics information, for example, in shape of further regularization terms that are motivated by the physics model. Yes, I can imagine that that there are incompressibility constraints. Yeah, exactly. A question from Jan Hesteven. One often observes that LSTM errors accumulate in time. In your case, that would mean the phase error grows in time. Do you see that? Do you see a growing phase error in time? Yeah, I do see a slight phase error growing in time. So in the advection equation, I noticed in earlier iterations of my training that the phase error was in general the problem, that the phase error grew. In this simple case, well, definitely not completely overcame it, but to a very large degree overcame it by doing a hyperparameter tuning. For the flow path cylinder, we again see that the phase is not completely matching the high fidelity. So that is definitely a problem. But for example, here for the flow path cylinder example, we can take 3,000 time steps, which is quite a lot without the phase error being a problem. So the phase error growth is not so large that it's a big problem. I would say, of course, that depends on the application you're looking at, of course. Okay, and then a very, very final question is, what are these 4 degrees of freedom? Can you say something about these 4 degrees of freedom in the reduced order model? Yeah, so if one is familiar with proper orthogonal decomposition, then I think the easiest way to imagine it is basically looking at it as when you project your high fidelity state onto your reduced space, then you get the parameter
in front of a series of basis functions in proper orthogonal decomposition. So in this autoencoder framework, you don't have a linear combination of basis functions, but you have a non-linear encoding. So it's slightly more abstract, but it is, at least to me, the easiest way of imagining it is seeing it as a generalization of proper orthogonal decomposition. In the case of the linear advection, here, where I have 2 degrees of freedom, we see these degrees of freedom evolving in time here. So they do resemble the behavior of the high fidelity problem in shape of periodicity, but otherwise there is no clear interpretation of them compared to the high fidelity state.
Okay, thank you very much. This concludes your talk and Q&A, Nikolaj.